All right, so today we are going to start chapter 13 from the textbook. And this is now taking everything we've done with objects in motion, and now we're going to understand the relationship between that motion and forces. More so, it'll be forces applied to some objects, which is going to create motion through Newton's second law. And we use Newton's second law to find our equations of motion. And typically for these systems, we have an object, there's forces acting on that object that's going to cause an acceleration if those forces aren't balanced. And then once we know our acceleration, we can use our equations of motion from before to solve for our velocity, position, etc. So today we're going to cover Newton's second law, which is F equals ma, and equations of motions for a system of particles. All right, so what are Newton's laws of motion? So the motion of a particle is governed by Newton's three laws of motion. And when we say particle, we don't mean it has to be a small point particle, but it could be an object that behaves as a particle, or where treating it as a particle still gives valid, I guess, analysis of its motion and the forces acting on it. So the first law, a particle originally at rest or moving in a straight line at a constant velocity will remain in this state if the resultant force acting on the particle is zero. So basically, a long way of saying a particle at rest wants to stay at rest, or an object at rest wants to stay at rest, and an object in motion wants to stay in motion. And here, motion doesn't just mean velocity, it also means the direction. So the speed and direction. You have to apply a force in order to change the direction of a moving object, which is changing its velocity vector, which is causing an acceleration. Newton's second law says if the resultant force on the particle is not zero, so the forces are not balanced, the particle experiences an acceleration in the same direction as the resultant force. So that means basically our equation, if some of our forces are not balanced, so not equal to zero, then forces will be proportional to some acceleration, and they're going to be in the same direction. And we know this proportionality constant is equal to the mass of whatever that particle or object is. So Newton's third law, mutual forces of action and reaction between two particles are equal and opposite and collinear. So collinear just means acting on the same line. So that was our example before for two blocks. Say we had particle A, some spring connecting them, particle B. Force of particle AB and the force particle BA. So this just says that FAB is equal in magnitude and opposite in direction, so it's equal to negative FBA. And so if we use lowercase f will represent internal forces, which will be more relevant when we deal with a system of particles. And then a capital F will refer to any external forces. So when we see capital letters will reserve for external forces, and lowercase letters will reserve for internal forces. So those are Newton's three laws of motion. And the big important one that we're going to use here is Newton's second law. And almost everything in Newtonian mechanics and dynamics you can derive from Newton's second law. So one more law we'll go through is the Newton's law of gravitational attraction. So any two particles or bodies have a mutually attractive gravitational force acting between them. And Newton postulated that the law governing this gravitational force could be written as the gravitational force, or the force due to gravity between two objects, is equal to the universal constant for gravitation times the mass of one object times the mass of the second object. Let's try to make those m's look the same. Divided by the distance between those two objects' centers squared. So here F is the force. G is the universal constant of gravitation. M1 and M2 are the masses of each body. And R is the distance between the centers of the bodies. So if we rearrange this equation so that one of the objects is a particle that we're doing an analysis on, or some object, and the other mass is the Earth, and the radius is the distance from the center of the Earth to the surface of the Earth, then the force we call this is just called the weight of the body. And that force would be equal to m times g, the acceleration due to gravity. So another important distinction for us to make is the difference between mass and weight. So mass is an absolute property. So an absolute property means it is independent of whatever gravitational field in which it is measured. Mass just provides a measure of the resistance of a body to a change in velocity. So it is, we can write by definition, or provides a measure of resistance of a body to a change in velocity. And this is defined by Newton's second law. If we rearrange Newton's second law, we can say mass is just equal to force divided by force acting on a body divided by the acceleration of that body. So if we have a more massive object, then we need to apply a larger force to get the same acceleration. Likewise, if it is accelerating faster, we will provide a larger force. So mass different than weight. Weight of a body is not absolute, and it depends on the gravitational field which it is measured. Depends on gravitational field in which it is measured. So we define weight. It's also a vector, and it's just equal to the mass times gravity, or the acceleration due to gravity. So let's just look
So,
at units quick. Yep.
while on the topic of weight and gravity, I've just been curious. So if two objects with the same mass, in the same gravitational field, but one was like more densely packed than the other, would the more denser one weigh more, or be the same weight?
If they had the same amount of mass, then they would have the same weight.
Even if they're more dense?
Even if they're more dense, if they're more dense or less dense, that just changes the amount of volume that they would occupy.
Okay, thanks.
So we can have, yeah, that's what this means by mass. Think of mass as just how much of a material, how much matter there is. And then volume or density would be how tightly packed does that matter. But mass doesn't matter how tightly packed that matter is or anything. If we consider the whole volume, whatever it's contained in, the mass is just how much of it is there.
Okay, thank you.
So we have two systems that we can use. These are the two major systems anyway that we can use. For the most common one is the SI system, where we have mass as a base unit and weight as a derived unit. So mass is a base unit. And weight is a derived unit. So what I mean by this is typically mass we'll just call grams or kilograms. So we don't use any other unit system to define mass. It's its own unit. So it's its own system, so we call it a base unit. So mass, our base unit for this is kilograms. And we calculate weight using mass and acceleration. So mass, or weight rather, would be equal to our mass times our acceleration due to gravity. So if our mass is kilograms and our acceleration due to gravity and our base units is meters per second squared, we call this as a force. This is the force newtons written in base units. Which is just capital N. So on Earth's surface, the acceleration due to gravity, say, is 9.81 meters per second squared. So this is the SI system. The other system would be that we will see problems with is the FPS system. So in the FPS system, weight is a base unit and mass is the derived unit. So that's kind of switched. So in this case, we have weight is the base unit and mass is derived. So our weight would be given in pounds. And mass is measured from this weight. And it would just be equal to our weight divided by that acceleration due to gravity in corresponding units. where g is equal to 32.2 feet per second squared. And so our mass then becomes our weight, pounds over feet per second squared, which we call a slug. So the term sluggish might refer to things that are more massive because they're more difficult to move. So mass is a slug in the FPS system, and it is equal to the weight in pounds divided by acceleration of gravity, which is feet per second squared. And like we said, acceleration due to gravity in the FPS system is 32.2 feet per second squared. So depending on what units the problem gives you, this is what they're referring to when they say pounds. Some books will call this pound weight and pound mass. For this, we'll just keep it simple, and we'll follow this convention where if we see pounds, that's referring to a weight, and the mass is slugs, and that would be the weight divided by the acceleration due to gravity. So in order to solve some problems, we need to consider the possibility that there might be multiple forces acting on a single body. So the motion of a particle is governed by Newton's second law, and it relates the unbalanced forces on a particle to its acceleration. Sum of our forces is equal to the resultant force, Fr, which is equal to mass times acceleration. So in this case here, Fr is our resultant force. So if we added up all the forces acting on our object, the resultant force Fr would be the vector sum of all those forces. And here the key word is the external forces. So if we look on the right-hand side, we have a particle right here. And we have forces F1 and F2. They're acting upwards and downwards to the left. And that's going to result in an acceleration. And that acceleration is going to be in the same direction as the resultant force, or the vector sum of those two vectors. So if we were to add vector 2 over here, we would see that the resultant vector is in the same line, which is exactly what's drawn down below. So in our diagrams, when we talk about free body diagrams, which we'll cover, we'll do some examples. But when we talk about a free body diagram is showing all of the forces acting on a particle or an object. So a free body diagram it shows all external forces acting on an object or particle. And we can equate this to our kinetic diagram, which shows the inertial force, which is our mass times acceleration, called inertial force, acting in the same direction as the resultant force. So our kinetic diagram this shows the inertial force. which is our mass times the acceleration of our body or our particle. So basically, we have a particle, it might have multiple forces acting on it. We can add those vectors to figure out a resultant force, and then we use our Newton's second law equation to figure out what our acceleration is if the forces are known. Another important thing to consider when we're solving problems is that we can only solve problems that have an inertial frame of reference. So this equation of motion, F equals ma, is only valid if the acceleration is measured in a Newtonian frame or an inertial reference frame. So what does an inertial reference frame mean? Let's think at the bottom, which of these are examples of inertial reference frames? So do we think a stationary platform is an inertial reference frame? Would that be a valid reference frame to do our motion analysis on? Yeah. It's sitting still. Most of the motion that we've been working on so far is with respect to a stationary frame, so yeah. The stationary platform is good. What about a satellite orbiting Earth?
Would we have to know whether or not it's accelerating?
Well, is a satellite orbiting Earth, is it accelerating?
Yes, because it's moving in a circle.
Right. So according to Newtonian mechanics, it has a circular motion. So according to Newton's laws, the velocity direction is changing. So it is accelerating. So this is a non-Newtonian or non-inertial reference frame. So we cannot stick our coordinates and do our analysis if our coordinates are attached to a moving satellite. And that is if we're looking at problems that are the size of the Earth. So yes, technically, if it's constantly falling, that means it's moving under some acceleration, so it's accelerating. So a car moving at constant velocity, how about this, the top right? So a car is moving, but it has constant velocity.
I think, yes, we can take that as an initial frame, like for reference.
Yeah. So the velocity is constant. It's not changing direction or speed. So that would count as an inertial reference frame. We can apply these laws of motion and we'll still get correct results. And then last thing is a spinning platform.
Unless it's spinning at a constant rate. If it's not, then we cannot take it as a reference frame.
So even if it is spinning at a constant rate, a particle anywhere on that reference frame or with respect to it would be seen to accelerate even if it's motionless because it's changing direction. So a spinning reference frame isn't a valid inertial reference frame either. So when we think of reference frames, our reference frame has to be a non-accelerating frame. So our frame of reference has to have a constant speed and direction, and that speed can be 0, which would mean that the direction is also constant. So typically, it's nice to do it with a fixed reference frame, but if our reference frame is moving at a constant velocity, then that is okay. Non-accelerating and non-rotating. All right, so now let's look at a system of particles. We can extend our equations of motion to include a system of particles, so not just a single particle. And this can include the motion of solids, liquids, gases for a system, as in statics. So in a system of particles, there are, like we talked about, internal forces and external forces acting on the system. So in In a system of particles, there are internal forces which we call lowercase fi for the force acting on each particle I, and external. And these are both vector quantities. So what is the difference between them? If we use the definition of mass, total mass of the system is equal to the sum of the mass of each individual particle. And AG is equal to the acceleration of the center of mass, G, of the particles, then we can write that m, total mass of our system, times the acceleration of the center of gravity, the center of gravity of our system of particles, is equal to the summation of the mass times the acceleration of every single particle. So for a system of particles, the sum of the external forces acting on the system is equal to the mass times the acceleration times the center of gravity. So here m, let's write a node, is total mass. So then the difference between the internal and external forces is the internal forces are the forces acting in between all of the particles. So say if we imagine this is a planetary system, perhaps, and gravity was acting as a force between all these particles. If we were to maybe want to model the motion of this cluster, then any external forces acting from outside that system would be the only forces we need to consider to determine where the center of gravity of this system is going to be moving. And this will come into play much more when we get into studying the motion of multiple particles, when we look at conservation of momentum, conservation of energy, and particle collisions. So what is the I next to the M? So I stands for particle I. So each particle just has a subscript I. So this might be particle 1, 2, 3, 4, 5, 6, 7, and so on. So in this case, if there's 11 particles in our system, I would just be summing from 1 to 11. So when I is equal to 1, that's referring to particle 1. When I is equal to 2, it's referring to particle 2. So that's all that means. I just represents the ith particle that we're doing our analysis on. So we're looking at a system of particles, whether it's 2 particles in a collision where I would just be 1 or 2, or if it's a system of particles all moving together, I is just counting through all of those particles. But this law always holds true for a system of particles. We think of a system. So let's recap quickly, and then we can look at an example. So Newton's second law is a law of nature. We call it a law of nature. It's experimentally proven, but it's not an actual result of an analytical proof. So we have yet to find an experiment that disproves Newton's second law for the realm of problems where Newton's law applies. It is still the best tool that we have to solve these types of problems. Mass is a property of matter, and it's a measure of the resistance to change in velocity. That's what we refer to mass and inertia. Mass is basically how much an object wants to stay still or keep in motion. That Newton law. Number 3, weight is a force, and it depends on a local gravitational field. So if we're in the absence of a gravitational field, an object can still have mass, but it won't have any weight unless there's a gravitational field acting on it. And we can calculate that weight by using Newton's second law equation and setting our acceleration term a equal to the acceleration due to gravity where that object is. And then finally, number 4, unbalanced forces cause acceleration. If the forces are balanced, then we have static problems, where some of their forces equal to 0, there's 0 acceleration, it's static. If we have unbalanced forces, then we have some of the forces are not equal to 0, this is going to equal some kind of acceleration, and this is basically the fundamental to all dynamics problems.